Okay, we're back. And with this one, we're doing some rotations. And this is kind of I think most would call it the infamous bowling ball problem. This appeared on the 2012 AP exam for mechanics. And this is number 3 on that year's test. And it was actually a ring that had like all 3 types of motion that you could have. It starts off initially as just sliding with no friction. Okay, so no spin, nothing like that going on. Just sliding. At time equals 0, according to this little diagram they gave, it starts to roll and slip. So it hits a patch here where there is friction. Friction creates a torque, and torques cause changes in rotational motion. So it starts to roll a little bit as it slides. And then eventually, after it slows down enough and gets enough grip, it does like just a normal roll, okay, rolling without slipping, no slipping whatsoever. So that's kind of the setup. It's a ring, so they gave us the moment of inertia. We know the mass of the ring, we know the radius of the ring, and they give us the coefficient of friction in the problem. And they keep it symbolic throughout this one. So let's just jump kind of right into this. It starts when you start the clock. Time equals 0 starts when you hit the friction and you start to roll and slip together. How do you handle that? What's going on there? And also the way they worded it, they wanted us to set up a differential equation. Okay, derive a differential equation for the linear velocity as a function of time, and then also for the angular velocity as a function of time. So right away, they make it sound hard by using calculus terms. Now keep in mind, think physically what's going on here. It's kind of like normal friction. It's going to be like a kinetic kind of friction. That's a constant force. This is actually a constant acceleration problem. But if we want to make it as a differential equation, they give us a Q. We have to use Newton's second law. Okay, so F equals ma for the linear part of the motion. And if we think of our force diagram in this, friction is the only horizontal force that you have. And that's going to cause, when you're slipping, in this first part, when you're slipping, heat's being produced and you're going to slow down. You're going to lose some kinetic energy. So I'm going to write this as a negative force. Friction is acting opposite the motion. Now friction is the coefficient multiplied by the normal force. And on a flat surface, the normal force generally is just the weight of the object, and that's it. Now the differential equation part of it, I'm going to go ahead and notice that the mass of the ring cancels out. A differential equation just means you have a derivative in it. Well, that's the definition of acceleration. Or the most general way of writing that down is as the derivative of velocity with respect to time, the rate of change of your velocity. We have our coefficient of friction and we have the acceleration of gravity. That's it. That's all they wanted for this. This is a differential equation. We just stuck in a derivative for the acceleration value. We're going to do the same kind of thing to get the angular velocity differential equation. But now for the angular velocity, for the rotational part of it, Newton's second law changes form a little bit. Torque is the equivalent of force. The moment of inertia is the analog of mass with rotations. And then we have the angular acceleration. Okay. Now in this case, keep in mind torque, in general, we define it as a force times a distance. Okay, that this is from the axis of rotation to where the force is applied, times the sine of some angle. In this case, friction is the reason why it's going to start to spin. Friction creates the torque. So we've got the friction force. The distance to the axis of rotation, which is the center of the ring, is just the radius of the ring. And then that radius line and the friction line, since friction is parallel to the flat surface, is an angle of 90 degrees. Okay. I suppose we could stick in mr squared is the inertia of a ring. They give us that. The friction, again, is just the coefficient times the mass of the ring times gravity, which is the normal force, and times the radius. And so we can make the same substitution. Okay, your angular acceleration is the rate of change of your angular velocity with respect to time. There's our derivative. That's how we set up our differential equation. And let's see, the mass drops out, and one of the r's, one of the radii drops out. And so all we're left with is coefficient of friction times the gravitational acceleration all over the radius. That would be the differential equation for the second part. Okay. Now, they kind of walk us through this. We're going to take what we have here, and they want us to derive the velocities now as functions of time. So I'm just going to go ahead and take that first one, okay, for the linear motion. This is from F equals ma, and just maneuver things around. We're trying to, to solve for things, we have to separate variables. We have to get velocity on one side. I'm going to multiply both sides by that dt, okay, by the time part. And once you separate the variables, you can go ahead and we can integrate. Now we need bounds. Okay, what the bounds? The clock starts at time equals 0, we were told. And we're just going to generically just let however many seconds tick off. On the velocity side, they told us that we had an initial speed. Okay? What we're really trying to find is what the v final is after so many seconds have ticked off. Well, this one's not so bad. The antiderivative on the left-hand side, the antiderivative of dv, we can think of like a 1 in there, would just be v. We're going to evaluate that. Now on the other side, we have some constants, and then we just get time, whatever the time interval is on that. On the left-hand side, don't forget that we have, when we evaluate these bounds, we stick in the top number and then subtract what you get when you put in the bottom number, the final minus initial. We have our final velocity minus the initial velocity is equal to that term. And so v final is the initial, minus mu g multiplied by the time. Because for the linear motion, that's that drag, okay, that rubbing that you have since it's slipping, and that's going to slow you down a little bit. Do pretty much the same thing with the angular velocity. Separate the variables. Time up on the other side. Once we do that, we can integrate. Time will more or less always have the bounds from 0 to whatever. But now think about the angular velocity. Okay, initially, it was 0. It was just sliding initially before it got to the friction part. Okay, so it's a different bound. It's not quite the same. It's decoupled from that linear velocity at the start. And then we're going and trying to find out whatever that final angular velocity is. And so if we go ahead and integrate, I'm just going to write down the answer. There's really not much in the way of steps here. And that would be our angular velocity as a function of time. Okay, that's all fine and good. Now let's see what they ask here. Okay, now they're getting into this transition from that region where you're rolling and slipping, okay, that total distance that you slide before you have no more slipping and it's just rolling. They're calling that distance big L. And they want to try to find what's the time it takes to slide, to go that distance, L before it begins to just roll with no slipping. Okay, well, this is where, again, we can kind of think in terms of, since we're trying to solve for time, maybe this velocity expression that we're talking about is going to help us. I'll just go ahead and write that down here. Okay. Now, the thing is, when you travel this distance L and you get to the point where there's rolling without slipping, what does rolling without slipping mean for us? Okay. First, it means there's no heat, there's no rubbing, so there's no heat being lost, or there's no kinetic energy being lost. It also means that we have some connections now between the linear quantities, linear distance, angular displacement, the linear velocity, and the angular velocity, and acceleration and angular acceleration. Once you travel and get that total distance L and you start to have no more slipping, your final velocity will obey and will follow this rule. Both motions are now in sync with each other. It's moving forward and it's rolling how we're used to seeing it. Okay. So I'm going to use that to our advantage. Okay. So that V final is V initial minus AT. That term right there is actually the deceleration that you have while it's sliding. But the time that we're looking for is when you get to the point where this expression between the two velocities is valid. I'm going to say the final velocity after that much time is r omega. Okay. And the thing is, we have an expression for omega, for the angular velocity. I'm going to substitute that in, okay, from the previous part and check out what we have. Let's play with this a little bit. In this term in the red that I have, the radius drops out. Okay. So now I'm going to go ahead and take what's left over on the left-hand side. That's going to be the initial velocity minus mu gt. What we're left with after it travels that distance is mu gt. I get the algebra right here. Collect terms. We're trying to solve for the time, for t. So if I add a mu gt to both sides, we get 2 mu gt. And finally, if we solve for the time, we have the initial velocity divided by 2 times the coefficient of friction times the acceleration of gravity. That represents the time it takes to travel that distance to the point where the motions are in sync. And we can use that substitution here, a connection between the two speeds. Okay. Now that we know the time it takes, it looks like they want us to figure out what that total distance is now. Oh, oops, apologies. They want how fast it's going after it travels that distance. Well, if we know that time and we have a velocity equation, let's just go ahead and plug and chug, I guess. The final speed is the initial speed minus mu g multiplied by the time it takes to travel the distance L. That's the time that we just found. I'll plug in the initial over 2 mu g. The mu g's go away. And if we look at that and just subtract that, we have 1/2 the original speed. That'll be the linear velocity, okay, the velocity of the center of mass of the ring after it travels that distance to begin just doing a normal roll. And last but not least, now they want us to figure out what that an expression for that actual distance that it travels. Because this is kinematics, because this is a constant acceleration, we have a distance equation, 1/2 AT squared, v initial times time, and whatever initial position you have. Now, the initial position that we have is 0, so that's where we started the clock. The final position, the final distance that you travel, that's the L that we're trying to solve for. I'm going to plug in the acceleration. Okay, now remember, it's going that this section here, it's sliding, and the acceleration was negative, it's slowing down. Coefficient times the acceleration of gravity, multiplied by time squared. Well, the time I'm going to use is the time it takes to travel that distance. I'm going to take that from part C. Oops. That's the initial speed over 2 mu g. That's squared. Then we have the initial speed multiplied by time. Use the same time over there. And last but not least, now it's just simplifying. One of these mu g's is going to go away in this first term over here and switch over to red. We're going to have a factor of 4 in the denominator, so 1/2 times 1/4 is 1/8. The initial speed squared, we're going to have a mu g left in our denominator. That's negative. Now the second term, we have the initial squared over mu g, and then we have a factor of 1/2. Okay. So that's looking okay. These terms are the same. We just have to subtract them now. So 1/2 minus 1/8, that's equivalent to 4/8 over there. That's going to give us 3/8 initial speed squared over mu g. And that'll be an expression for that distance that we travel. Oh, this is why I suspect that back in 2012, the average score on this was probably really low. This is a tricky problem. You really have to think it through. In my mind, the key is, first, understand that it's constant acceleration. It's a constant friction force that we deal with when we talk about rolling and slipping or rolling without slipping. It's either a kinetic friction or like a static friction. So we're just basically using kinematics all the way through this. Okay, that makes life a little bit easier. For me, the key, I think, is really coming in here in part C. When they talk about sliding that distance L, you make that transition from rolling and slipping to the no slipping. And realizing that by the time you travel that distance, these relationships over here between the two motions are connected. And we can start using these expressions at the end of that travel over that middle section there, okay, where it's, you have some slipping going on. So I hope this helps. Go back to parts that you want to hear again and see again, and try to make some sense out of this. But yeah, I hope it helps. Rotations, it's kind of fun, but it's also challenging at first because you really aren't familiar with rotations when you start doing this. But hopefully this made some sense for you. Thank you, and we'll see you later.